So last video, we introduced a new variable force. We're going to keep doing that with another variable force that you will use a lot in modeling stuff physically, and that's the spring force. We called it the spring force because you can demonstrate this very easily with a spring. But really, this force is useful for anything that oscillates, anything that swings back and forth around a fixed point in 1, 2, or even 3 dimensions, behaves like a spring, can ultimately be modeled like this. And that's basically everything in the universe, because anything that doesn't obey a spring force law blew up a long time ago, right? So what we need is a model that always opposes the direction of the stretch, right? Because a spring, if I stretch it outward, it's going to pull inward. If I push it too far inward, it's going to push outward. So I need this to go like the negative of the displacement vector. So that's why this negative sign is here. The negative means always pull me back toward equilibrium. But I also need this force to get stronger as I stretch the spring farther. So if I stretch the spring and keep stretching, it gets more difficult for me to pull it farther because the force is getting stronger. So that's why we have a delta R here. So this delta R just means the displacement from equilibrium. So we're taking R equals 0, the origin, to be our equilibrium point where the spring likes to live. And then it also needs to depend, and then the force also needs to depend on the spring itself. Some springs are very light, like if you take apart a pen, a writing pen, you've got a very weak spring in there. If you sit on a mattress, you're sitting on a lot of very stiff springs. If you go, drive your car and your wheels kind of jostle up and down with your hydraulics, those are incredibly strong springs. And so the K here is something we call the spring's stiffness. It's what we call an extensive property, meaning it depends on the spring itself. This is unique to every spring. You can think of it as being dependent on the material, the coils, the windings, how small it is, how many windings there are, how long it is, etc. You can break this down into other factors, but for right now, we're just going to call it K. So what I've done in the description for this video is I've included a link to this code that takes care of a spring animation. Now, this is longer than the last couple of codes we have worked with because there's more going on. There is a longer setup because we have a ball and we have a spring, and we'll get to that in a minute. But what I want you to focus on, where I want your eyes to go, is down here to the loop, because I want you to notice that this is the exact same setup that we have had before, right? We are going to calculate the force. The difference is now it's the spring force. I don't have weight, I don't have drag. I could add weight and drag, and I encourage you to do so after the video. But the important thing is I'm calculating the force. The only thing I've changed out is the force, because the rest is the same, right? I update the momentum, and then I update the position. And so this is just a recap. This central engine here, calculate the force, update the momentum, update the position, that is always the same. The universe will always operate on that. The only thing that changes is how we calculate the force. So let's go ahead and fill this in. Let's recap the momentum update. So the way I update momentum is I take the old momentum and I add to that the net force times dt. And then I need to update the ball's position. How do I do that? Well, I take the old position and I add to that the momentum times dt divided by the mass, right? That central engine will always be the same. That is never going to change until we release new physics, which has not happened since the advent of quantum mechanics. So until you take quantum mechanics, this is always the same. You can always rely on this being the central engine for everything you do in a model. So let's go up, let's talk about the ball we're creating. So I need to give this ball an initial momentum. Let's just call that 0, 0, 0. It's always nice to start from rest. We'll give it a mass. Let's say 1 for right now. We can change that later. Give it a radius. We're going to have it make a trail, because I always like to leave a trail in the animation so you can see where it's going. And we need to give it a position vector. So the only thing I need to do is make sure that this magnitude is bigger than the spring's L0 value. So let's go down and pick L0 first. We should probably do this a little bit out of order. Here I'm going to create a spring. This is new. We have not made a spring before. We've only made spheres before. But a spring you can create using the helix function. Helix is just a fancy word for spring. I don't really know why they didn't just call it spring, especially since being developed for a Physics 1 class, the purpose of this helix is to model a spring. But maybe they're trying to appeal to the life science students in the rooms who are working with double helixes. I don't know. We're going to anchor this thing's position at the origin, and we're going to give it an axis of ball.pos. So what that's going to do is it's going to say one end needs to go here, the other end needs to go here. Like we saw before, we're going to give it a spring stiffness. Again, let's start with 1. And L0, this is the spring's equilibrium length. So you remember we have this delta R. Delta means the distance from your rest position. So this is where we want the rest position to be. Let's just pick an L0 of 1. So it's going to have a natural unstretched length of 1. And so let's give our spring, let's give our ball here a little bit past 1. So let's make it 1 and some change, 0, 0. Let's actually see what that does. I'm going to comment out the rest of this, so we're not going to animate just yet. We're just going to create the visual. This is what this visual does. So first it creates a ball. The ball is located to the right. So it's over here on the right-hand side. Then the spring starts at the center. It starts at the origin, 0, 0, 0. So that's the starting point here. And it goes to the ball's position. Well, where's the ball's position? Well, it's right here. So it looks like the spring is wrapping around the ball. This is just a cool little trick to get the spring to go to the ball, right? You already have the ball's position defined. Just reference it here under the spring's axis. Okay, now comes the fun part, making the animations. Let's go and uncomment this. So I need to calculate the force here. So the force is negative to get it pointing back toward equilibrium. Spring stiffness, so this is negative K. And then I need this delta R vector. So remember, a vector has a magnitude and a direction. So the way we're going to do that is we're going to calculate the magnitude of the stretch. dr is the amount of stretch. And then I need the direction. Well, the good news is I already have a direction on this. I can just take the spring's axis vector and turn that into a unit vector. So VPython has a built-in function called hat that will turn a vector into its unit vector. It just takes the vector, divides it by its own magnitude, and then spits out a unit vector. So what I need to do is calculate dr. I need to figure out how far this thing has stretched. So if I think about that, what I want to think about is I have the magnitude of the ball's position minus the rest length, right? You imagine if this were 1, 0, 0, that would exactly match in magnitude this unstretched length. The thing would not move at all. But if I make this 1.1, I'm putting it 0.1 off from the equilibrium position. And so what I can do is come down here and I can just subtract those two. So I can say I'm going to take the magnitude of the ball's position minus the rest length, right? So I'm sort of comparing how far out the ball is from how far out the spring likes to be. All right, let's click run and see what happens. L0 is not defined. Oh dear. Oh, that's right. This is supposed to be the spring.L0. Okay, I found a typo there. I'm hopefully going to remember to fix that before my next class when I'm actually using this, because there is no better way to sow mass confusion than to put a typo in a code that you give to students. And sure enough, notice what happens first. Because it's too far to the right, it gets pulled inward, but then it overshoots, goes too far to the left, and gets pulled outward. So what I can see in this animation, it is oscillating around the location x equals 1, because it wants to be at this unstretched length. It wants to have a dr of 0, and so it's oscillating between a positive dr and a negative dr. And then it overshoots again to a positive dr, and then back to a negative dr. And it's going to keep repeating. Unless I put in a drag force, it's going to keep repeating over and over and over again. I could put in a drag force. I'll let you do that. But what I love to do with this problem is, first you can play around with this a little bit. Like maybe I make this bigger. So stretch it to 1.5. And you notice there I get a much bigger oscillation here, right? So it's going to stretch, it's going to compress farther and stretch farther with each of the oscillations. I can also play around with the stiffness value, like maybe I make it twice as stiff. Let's see what happens there. So I make it stiff. I notice it's yanking back and forth a lot faster. Let's go up to spring stiffness of 10. Oh, definitely going faster there, right? But you know what? I've got this 3D environment. The really fun thing to do with this is to take this and move it in 3D. So like maybe I make this a 1.5 and a 0.5. And now I'm oscillating around along this axis here, right? I'm not just oscillating along the x-axis anymore. I'm oscillating along the x and the y. It's still only in one line, right? It looks like a pool cue there or something. It's still only oscillating in one line. So the really fun thing to do with this is start changing the momentum. So maybe I give it a little bit of a nudge in the vertical direction at the beginning. And now I've got motion in the x and the y. And now I'm oscillating in 2 dimensions. Now suddenly this is really cool, right? This, I mean, I would love to try to get this set up in lab sometime. I'm not sure how to do that without gravity becoming a factor. But what's really cool about this now, I'm oscillating in 2 dimensions. And this is why it was important that we treat these things as vectors down here. Because remember, it's not trying to oscillate about a specific point. It's trying to oscillate about a specific length. And so what's happening here, the spring keeps trying to return to the equilibrium length L0. It doesn't care what angle that happens at. And so this thing is free to rotate around in the XY plane here, trying to get back to an equilibrium length. And well, we're in 3D. There's no reason I can't put a Z component to my momentum there. And now what's going to happen, I can rotate this around. This thing is tracing out a trajectory in 3D. I think it still sticks to a plane. I think unless I do something a little bit different in the Z direction, yeah, that's going to be confined to that plane. I wonder if I can... I don't think it's going to matter if I change this. No, it's not, because nothing is making it rotate around. There's no external torque making it rotate. So no matter what you do with these combinations, this motion's always going to be in a plane, which is kind of cool. Later we'll talk about why that is in terms of what's happening to the angular momentum. But this is the kind of fun stuff that I love to watch in 3D, is coming up with these fun initial conditions and watching the thing trace out a very unique trajectory.